Hello, my name is Shahriar Ebrahimi. I'm a postdoc researcher at IDS NCBR. I'm here to present our paper, From Interaction to Independence, zkSNARKs for Transparent and Non-Interactive Remote Attestation. The other author of the paper is Parisa Hassanizadeh, who is a PhD student in Polish Academy of Science and a PhD researcher at IDS. Before going through the paper's idea, I'll give you a brief introduction to remote attestation in general. Basically, RA is a protocol in which you, as the owner of the device, want to verify the authenticity of certain parts or functionalities of the device without having the physical access to it. Usually, the device acts as the prover, while the verifier is the privileged owner of the device, who has also some accesses to some certain knowledge about the device, such as peer-shared keys or some reference measurements. The protocol is interactive, of course, and the verifier sends some challenges and expects the correct responses from the device. One of the main concerns in traditional remote attestation protocols is the continuous trust on the verifiers from the user's side. Users have to always trust the verifiers to be honest through the lifespan of the devices. In addition, devices also have to ensure that challenges are from an authentic verifier to prevent attacks like man in the middle. Another limitation is the fact that the entire protocol always depends on trusted party. This results in single point of failure in protocol, causing concerns in the overall system's availability. This combined with the fact that we require unique pair of challenges and responses per device limits the scalability of the system in general. As you can see in this figure, the number of messages transformed by one entity in the network is directly affected by the number of attestations multiplied by the number of devices. Previous work usually try to address these issues by introducing additional entities to the protocol, or that also introduce additional trust assumptions or use impractical methods such as secure smart contracts or trusted event triggers. So to address these issues, we propose a new method for remote attestation that follows two main principles. The first one is the transparency, which means that anyone can publicly verify the correctness of the attestation result without having any prior knowledge about the device itself. And this should be also trustless, which means that verification requires no trust on any third parties, and also it has to be done independently without any knowledge given from anyone. In addition to this, the proposed protocol should be also non-interactive. So this means that we have no direct interaction with the device or the manufacturer to verify or attest a device. And between the device and the manufacturer, we don't want any interactions between them also. To achieve this, we also propose another concept as the global challenges, meaning that one challenge will be used to attest all of the devices during a certain period that we call it attestation interval. This makes it also very suitable to be built on top of data structures like blockchain, and achieving this will also result in some inherent resilience to DOS attacks. We call the protocol Zira due to the fact that it uses zkSNARKs for remote attestation, and the protocol follows 4 phases. The first phase is the setup phase that is only done once and is done by the manufacturer. The second phase is the update challenge phase that is done periodically. The manufacturer broadcasts some global challenges. And in the third phase, devices use the latest global challenge to provide their proofs, and this is done asynchronously, and so the devices can miss multiple challenges, go to sleep or wake up and then attest themselves. And the last phase is the verification that is done independently and can be done by everyone. During the setup phase, the manufacturer calculates all of the possible responses for each device using these series of global challenges, and then commits to these responses by calculating the hash of public key of the device concatenated with challenge and concatenated with the response itself. Then the manufacturer builds the Merkle tree using these commitments, and finally builds another tree on top of these trees that are built for each device, resulting in one big Merkle tree that contains all of the commitments for all of the devices. And just one keynote here, that these commitments have the both properties of the binding and hiding. We have the public key and also the challenge CI in each of these calculated hashes that act as the binding property, and also we have this unknown response before revealing that act as the hiding property. So basically, with such a structure, we kinda transform the problem of attestation to the problem of knowing the opening of certain commitments that belongs to the Merkle tree. And this way we can make it publicly verifiable. Okay, after publishing the Merkle tree's root actually, the manufacturer periodically just broadcasts the global challenges per attestation interval, and we show in the paper that this phase also can be done in an MPC manner to achieve a threshold global challenge. This improves the security of the protocol, meaning that in case of any security breach in the manufacturer, we still have the possibility to hide the possible all of the future challenges. So we make sure that still the setup phase shouldn't be repeated again. During the attestation phase, the device just simply proves the knowledge of certain response, that is RI, that when concatenated with its own public key and latest global challenge CI, this whole thing will result in an opening to a commitment that belongs to the published Merkle root. Just note that this proof is generated by the untrusted part of the device, so we don't need any trusted execution environment for generating this proof. And these proofs are actually can be outsourced to even untrusted devices. As said, the verification of zero is just transformation to the problem of verifying whether the device has knowledge about certain opening to a commitment within this Merkle tree. Therefore, this verification can be done by only using public information such as the Merkle root and only the latest challenge and the public key of the device. And the verifier doesn't need to know the logic behind achieving the correct response from the challenge, or care about any tracking, for example, managing some previous responses of the device, or any knowledge at all about the device. We've provided a security analysis of the protocol against different threats from an attacker in probabilistic polynomial time model. But basically, for all of these attacks and threats, we mainly rely on the soundness property of the underlying proving system along with the security of the hash function that we've used for these commitments. We've implemented all of the parties in Zira in an open source GitHub monorepo. The link is available in this slide, and while the manufacturer side was implemented in JS, we designed a fully automated verifier in Solidity and deployed the contracts on this Sepolia testnet of the Ethereum, and executed all of the rounds of the protocol in different transactions. The links are and the details of these transactions are available in the paper. And finally, we used Circom and SNARKs for the device to generate proofs of attestations. We used different setups to showcase just the practicality of Zira in different scenarios. For this, we provide experimental results on a mid-range laptop and 2 IoT-compatible boards, and evaluated their performance while acting as the prover in Zira protocol. Experimental results show that obviously Zira has significantly better scalability results compared to the state of the art, simply because the number of transmitted messages by any entity in the protocol is at max equal to the total number of maximum attestations, and it is independent from the number of devices. This is in contrast with the previous work where the total communication complexity of the trusted parties, such as the proxy or some brokers, it just scales with the number of attestations multiplied by the number of devices. In terms of computational complexity in the prover side, Zira obviously requires more complex computations because it calculates this zkSNARKs proofs. But on the bright side, this complexity does not really have effect on the overall performance of the entire protocol, because these proofs are per device and only per attestation. So each device does this proof once per attestation. However, in the previous work, we have trusted parties such as this proxy verifier or the broker that have some sort of calculations or processings for each attestation per device that must be done by these proxy verifiers or the broker. This has the direct effect on the scalability and attestation per second, the maximum attestation per second that the network can achieve. However, in case of Zira, we don't have such a process. But these results show that although Zira is highly scalable, it has computational demands on the device. In conclusion, we can see this work as a showcase of how zkSNARKs can be used to tackle the traditional challenges in cyber-physical systems. For example, the high potential to increase the scalability by just removing the interactions in the protocols and make them more suitable to be built on top of more distributed infrastructures such as blockchains. And the possibility to resolve trust issues in these protocols are also some examples in here. However, the main challenge is the computational complexity that these proving systems demand on the prover side, which unfortunately in different IoT scenarios, these devices have limited and constrained resources, which leads to the path for future research and development to achieve more efficient implementations for proving for different proving systems, using and working on the hardware accelerations to make them more energy efficient, and also we need to employ more modern proving systems which have lower complexity in the prover side, such as a Spartan. And in general, we will see these trade-off between the proving complexity, the proof size that it directly affects the communication cost, and the verification complexity, which may not be very important in terms of IoT in IoT scenarios, because usually the verifiers are some centralized servers in here.